Hi, the topic of my project is personalized fashion recommendation, and I have built this using the H&M dataset containing customer transactions with rich product and user features. So, the structure of this presentation is as follows. It starts with the problem statement and objective, and then a little about the dataset with the description of how it looks like, what all attributes does that have, and a few plots to visualize how the data is distributed. Then I'll start defining the baselines for the problem that I used for reference, and then I'll move on to the intuition for the improved approach that I used. Then I'll dive deeper into the implementation details like the data preparation, discussion about the model, and I'll finally conclude with the evaluation and results. So the problem statement is from H&M, which is a global fashion retailer serving across multiple markets, and it seeks to develop a personalized recommendation system that is able to predict the top 12 fashion articles each customer is most likely to purchase in the upcoming week. So the objective for us is to build a recommendation algorithm that is able to predict the fashion articles that each customer is most likely to purchase in the coming week based on their historical transaction data, product features, and customer demographics. So, this is how the dataset looks like. It consists of three files and a folder. So, the transactions data file contains around 31.8 million purchase records spanning across a period of 2 years, and it is populated with fields like customer ID, article ID, transaction date, price, sales channel ID, etc. And then is the articles data, which contains the information about the fashion articles. There are around 105,000 unique fashion items, and this file is populated with the attributes like product type, product group, graphical appearance, color group, perceived color, department, index group, and etc. Then there's the customers data file, which contains around 1.37 million unique customer attributes, again populated with attributes like age, postal code, which is a hashed string, and then details like is the customer part of the fashion newsletter subscription, are they an active club member, and there's another folder containing high resolution images for each article organized by the article ID. So this slide contains a few plot to visualize how the data distribution is. So here we could see that there are a lot of users with lesser number of purchases, and there are relatively lesser users with higher number of purchases. The same here, we could see that there are more users with who have purchased ha- higher unique item lower unique items like this we could see that there is a spike here which says that people tend to buy more popular items, and this decreasing trend suggests that with decreasing order of popularity is what higher number of users tend to buy the fashion articles. So moving on to this plot, we could see that there are a huge number of people who have just bought very few items, or like they have just shown up to the store once and have had minimal transactions. And also we could see that there's almost an even spread of users who have like subsequent purchases, and also kind of loyal customers who turn up to the store after a long time. This shows that again people tend to buy more popular items than unique items. This is a temporal distribution, or like a time series curve showing how the transaction volume has changed over time. So we could see there's some sort of seasonality here around the month of July, and the seasonality kind of repeats over the years. And this is the weekly transaction volume. Again, this is the user purchase activity distribution and item popularity distribution. We could see that there are some items which are very popular, and the more number of items which are like less popular. So moving on to the baselines that I used. So I used a popularity based baseline. As we could see, fashion is an industry which is highly driven by popular items. People tend to have a higher demand for fashion articles that are uh, popular in a particular period of time. So also, due to that behavior, popularity captures good market signals like trending items, bestsellers, capturing broad customer preferences. And also for very sparse data, this is a great starting point for building a recommendation algorithm. The next thing that I used was user-based collaborative filtering. So in fashion, we know that people tend to uh, get inspired from or follow fashion preferences of other people, and it is also a great point to start with as it directly captures personalized preferences through similar purchase patterns from other users. So, given that this is a really big data set and it would be really compute intensive to run multiple experiments to test on with different models, so I had decided to downsample the data set to bring down the size of the data set so that I could get a smaller sized data or a smaller volume of data which is equally representative of the distribution of the bigger data. So these are the steps that I follow to downsample. The first thing is I selected a temporal window, a window of 12 weeks, in which I used 11 weeks data for training and retained 1 week of data for testing. So this reduced my data size from around 31 million transactions to around 3 to 5 million transactions. Then for keeping the data more rich, as we observed that in the previous from the previous plots, I kept mostly the active users who have had who have had purchased in the validation week, so that we are able to model the customer preferences in a more better manner. And then implemented item frequency filtering, which retained items with greater than 5 purchases. This is just to make sure that the dataset that I have is a good representative of a user's purchase preference, so that if an item has a purchase history, it's easier to understand the user item interaction, and we could better model users' preference based on item purchase history. So similar to what we did in the previous assignment, this dataset only contains the positive samples because it's a transactions dataset. So it contains all the details of users who have had transactions. So I had to do negative sampling to bring up negatives in the dataset. So after doing all these filtering, the final dataset size boiled down to having around 3 to 5 million transactions, with training data set around 2 to 3 million candidate pairs, and the final training data set around 500,000 to 1 million samples. So this is the plot of the training data set, which contains around 40% of positive samples and 60% negative samples. This is sampled in a way that it is able to understand users' positive preferences, at the same time able to understand what user doesn't like, so that there is a balance, so that there's a balance in the data set, and the model is able to understand users' positive and negative preferences. So these are the plots for the training and the validation sets. So we could see the distribution of users per item and distribution of positive labels per item. These curves tend to follow a similar pattern to what we saw for the bigger data set. So we could say that this is a good representative of our bigger data set being a smaller sample. This is a small visualization for training and versus validation data set. It is just to see the distribution of training samples against the validation sample. So moving on to the intuition for the improved algorithm. So the baseline algorithms do not leverage the rich features about the users and items like the demographics, item features, colors, perceived color, etc., and the image features. These features could be used extensively to model user preferences better and understand their purchase habit. So the intuition for improving the solution does exactly something similar. It uses the information that we get from user interactions, item collaborative filtering, extract those features, and then build a candidate pool based, and from that candidate pool we can use the rich features of those candidates to again then rank the best uh, fashion articles or the best items for users, and model the problem as a ranking problem. And so these features tend to help learn the hidden semantics of user preferences and could scale well for cold start users also, since we are using user features and item features to develop and understand the user preferences. So for cold start problems, when there is a new user, based on the user demographic features and similar user purchase patterns, we could give good cold start recommendations to new users, is what I hypothesized. Another important thing that the baselines don't use is that this approach also uses the temporal nature of the transactions. It extracts information from the timestamps of purchase and gives additional data for learning the purchase behavior of the user. So the method description starts with the data preparation, and I did already talk about that. So some nuances in the data preparation was we I did a stratified sampling of the users in the training set to make sure that we have users from all sorts of purchasing behaviors. And to keep the data set realistic, I also have 15% cold start users. And for managing computational constraints, vectorization and downcasting of variables was performed, because even though this sample is a smaller sample of the data set, but still the amount of computations for computing the user interactions, user item interactions was really large and had to deal with a lot of sparse matrices. So downcasting of variables and vectorization saved a lot of computational time. And since I had to go across use multiple models and run multiple experiments, so all the subsequent stages or intermediate stages of data processing was saved as Parquet files, so that I could start from those Parquet files for uh, subsequent multiple experiments. So the stage two starts with candidate generation, something that I talked about before. So the candidate generation idea uh, is basically an idea to generate a candidate pool among the available set of articles which the user is most likely to buy. So the idea is, we do know that from the dataset we have a huge pool of articles available, and for running an algorithm across all the articles is really compute intensive. And we definitely would know that if user does not have any sort of interaction history with items of similar features or items of similar interest, the user is not going to buy them, and that sort of compute is or that sort of computation is essentially not required, and we could avoid that. So the idea is to generate candidates which are like potential solutions or potential articles that a user would buy. And for generating those candidates is use where we use the collaborative filtering idea to generate candidates. So repurchase strategy is one of them. So this is something that I implemented here in the notebook, which checks the repurchase strategy, identifies users who have previously purchased, and scoring them based on recency, effectively capturing user loyalty patterns and repeat purchase behavior. So, next is the popularity based strategy. which is again kind of the base, similar to the baseline that we used. We recommend the globally trending items by aggregating sales number, unique buyer counts, recent purchase trends, and coverage of items in current demand. The co-purchase strategy is like a complementary item relationship strategy, something that we could say these items are frequently bought together. So I used Jacquard similarity to here in this part of code to get the, this part of code I used Jacquard similarity to get uh, complementary items that are bought together, and especially those items that are bought together like shirts and pants, they receive a higher purchase score, a co-purchase score, enabling cross-selling recommendations. This is again a really great strategy, because this is something that the popularity based and the user based strategy did not use. The next thing is I used user KNN strategy here. So this this strategy found similar users based on purchase history overlap, and then recommended items purchased by similar users, effectively leveraging collaborative filtering principles to handle diverse user preferences patterns. So this is basically the one that accounts if you tend to follow, or a user tend to follow some other users preferences, then the recommendation for those users could be similar, and essentially their buying habit is similar. So this is the strategy that helps us generate candidates based on other users, or uh, we could say like similar users buying preference, and bring that to you. Let's say if you have a buying habit or buying preference similar to other user. So next thing is the category based. So this is a simple strategy which says the users purchase preferences with items popular within a category. So this checks out the user's purchase history and gets the items from that category if the user has bought. And the implementation for this is here. Oh, this is the use KNN collaborative filtering. This is where we use the user metrics and compute cosine similarities, not Jacquard similarity. Use cosine similarity to get the user KNN to find similar users and build user preferences based on similar users. The next strategy is the category based recommendation, that uses category preferences from users history. So this is where we use the category preferences. We tend to yeah group by customer ID and product type number to understand which category to merge data based on the categories, and then count the user top categories, and then understand which categories the user tends to buy more products. And text similarity strategy is simple, since we also have text features corresponding to each products text features corresponding to each products in terms of their descriptions. So we could use that. So I used it here, text similarity. Yeah, so this is from another file. The implementation of this is here, text features. Yep. So this computes the user text preferences using word to vec embeddings, similar to what we did in our previous homeworks and assignments. So next we move on to the feature engineering part. So now from the given data that we have user level features like the demographics and total purchase count, unique items purchased. These things are the features that we could get from the user behavior, and then we could also extract temporal features like days since first purchase, days since last purchase, average days between purchases. These are like some sort of pre-processing done on the already existing transactions data to get these items. For item level features, we use product characteristics, performance metrics like categorical attributes, popularity metrics, temporal item features, and recent performance indicators. For user item interaction features, we encode relationships between specific users and encode relationship between specific users and items, including purchase history indicators, category alignment, price compatibility. All of these things were calculated during feature engineering, and the code for that is present here. So this is where we save all the recall strategies and save the candidate pool that we could get for every user. This part starts with the feature extraction. We load the process data which contains all the candidates, and then move to getting the user features. Some user features, we do some statistics like mean price, standard deviation of the price, the min max date, and using this we could generate all the features in here. This from the features we can also get recent activity features. We could also generate flags like was the user active last week, and we could get the diversity features, a bunch of features that I implemented for user level, item level, user item. So for the image features, I used Fashion Clip. Fashion Clip is a pre-trained model which is uh, we could say it's a text and image model. We could use text embeddings too, and text data too, and image data too, but I used Fashion Clip only for image data, where I generated embeddings of the article images using the pre-trained Fashion Clip. So it gives out a 512 dimension image embeddings. This is to ensure that we do not miss out on any features like the texture of the article, or the shape of the article, the fit of the article. And the choice of Fashion Clip was obvious because this was trained on a huge data set containing fashion products. And for the text features, I used the complementary visual features for the text features, I used the semantic information from the article descriptions, and using TF-IDF factorization and dimensionality reduction. So dimensionality reduction was performed using PCA, and we created article embeddings along with image embeddings. So now that we have prepared a data set, and we also have prepared the features on which we want to train, we start with the method description for training the model. The first part was I started with the gradient boosted machines. Uh, so these are like boosted decision trees, and I used various aspects of them. The first For the first model, I modeled the whole task as a purchase classification task. So it's like a binary classification where given all given all the features and a given user for an article, uh, will will the user tend to buy that article or not. It's like a 0-1 classification. And then the second variant was a light GBM ranker, which was basically trained on a lambda rank objective or a ranking objective. So lambda rank is kind of a we could say a loss function which helps us to optimize the ranking. And then again lambda GBM ranker with a different ranking objective. Then another GBM rank, a light GBM classifier, but this time again trained with the binary log loss, but was rather deeper or bigger than the previously trained light GBM classifier. This is just to ensure that if I'm able to capture more complex features by using a bigger model. The second part of the model training was to use neural networks. So I use some sort of a three tower neural network, let's say, if not a three model neural network. So every tower was trained independently for re- to understand the inherent latent features based on the user's latent features based on the user features. So tower 1 or the model 1 takes around 43 length user feature vectors and trains a two-layer multi-layer perceptron in this fashion with batch normalization, ReLU activation, and a dropout of zero point 0.3 to produce a 128 dimensional vector. So this is a user embedding which has uh, hidden user preference semantics based on the user features. Similarly, for another model for item features, which again understands the hidden semantics of the item preferences based on the item features. And then another model which basically I used it to compress the dimensional image embeddings from fashion clips. So it was a 512 dimensional image embedding. So I again used a two-layer MLP to bring it down to even smaller or yeah, even smaller dimensional embedding, again with the hidden semantics of the aesthetic and style of the article image. Then using all the three embeddings that we get from these three different models, I trained those embeddings on a fusion layer. So what this fusion layer does is basically it concatenates the embeddings from all these three different models, and now this is our super embedding. So this is where the cross learning, or we could say uh, user item preferences or user item preferences and the hidden semantics of relationship between user item preferences is learned, as we have the user semantic features here, the item semantic features here, and then we train a deep learning network to uh, on a binary classification task with binary cross entropy loss. So this whole training model was again posed as a binary classification task, and these are the training specifications for that model that I used. This is a small visual representation of what happened. So this is the user tower. This was trained on 43 features and gives out trained this is the data with 43 features, and it was trained on a two-layer MLP with which gives out a 64 dimensional embedding, again with the item tower. Oh, sorry, there's a small mismatch in this. So this is basically like this was trained on 43 features, and this was basically like 43 to 256 and 128. This is like the item tower features, which started with 29 features, and then it for the model it scaled up to 128 uh, sized MLP, and then gives out an embedding size of 64 dimension. So this is the item tower which gives out the 64 dimension embedding. This is the user tower that gives out the 128 dimension embedding, and the image tower again gives out the 128 dimension embedding. What is happening here is very important. We concatenate these embeddings, and this fusion MLP is what learns the hidden semantics of user item preferences based on the user features, item features. So the results based on what the competition or the H&M recommendation task was supposed to be. It wanted to evaluate the mean average precision at 12, so I kept the same as my evaluation metric. So along with that, I also used precision recall and NDCG for evaluating how good the model performs. So the model predictions were ranked by MAP12. The final ensemble combining the best performing model. So I also tried to combine the predictions from light GBM ranker and light GBM classifiers along with this model, but based on the results that I got, I saw that the neural tower performs better than uh, the light GBM models because it's able to better understand the hidden semantics of user item interactions. So this is the best MAP at 12 that I could get, and comparing it with the baselines, for the popularity baseline, I received this score of MAP 12, and the implementation for this is provided here at the top of the notebook, where I start with the exploratory data analysis, pulling out some plots for the data, and this is where the baseline models are implemented. This is the baseline one, which is the popularity based recommendation. This gives you a score of MAP 12 626, and this is the user based collaborative filtering result, again 625.625 MAP. And the whole training process of the model starts from stage 4, which is from here. Yeah, model training. So I start with defining some configs and then load the data from Parquet files, the training features, the val features. Then we start out with creating the labels. Since we have the training features, which is like all the positives, and the train transactions, which contains all the transactions, so we need to generate positive and negative labels. So this code essentially takes care of that, prepares the data by generating samples and labeling them with 0 and 1, because both most of our tasks around ranking and binary classification would sorry, most of the are couple of tasks for light GBM, and the neural tower is for binary classification, so we would need points with data points with labels. So this part of code takes care of that. It also takes care of the negative sampling. So this part of code only creates labels for training data. This chunk of code creates labels for validation data, and this part of code generates the validation labels, validation users. Now we define our models somewhere around here. Yeah, so we start with the light GBM training and re-ranking. This are this part of code contains light GBM implementation, where we load data, we do train test split, and then we start initiate the training. These are the light GBM configs that we use for training. And yeah, this is a very important thing that I saw about the feature important analysis. Since we are training a tree based model, it gives out a good feature importance. So we could see that these are like the co-purchase score, distance popularity score, these things receive a really good feature importance. The user score, KNN rank, in which says that the features that we used for candidate generation or generating the candidate pool were actually one of the most deterministic features in training the model and then understanding the user preferences. And similarly, in subsequent stages, we implement the neural network model. So this is the binary cross entropy loss. Yeah. So these are the list of references that I used, and a few directions in which there could be future improvements. Like we could these are some directions that I explored while trying to develop solutions, but I was not able to implement it because of computational resources. As you could see, this image tower, item tower, and user tower. So I could not use image tower along with item tower and build a two tower model and test its performance due to computational constraints. And but this again is a great idea. uh, I use the image tower separately without the item tower because I wanted to understand how much of an impact the image embeddings make. And the next thing is we could use sequential recommendation with transformers or attention based models. Again, this method would need higher compute and would need more time to train the model, and it's difficult to run multiple experiments, but it's again a great place to continue this or improve further from this model. And again, the use of graph neural networks also tend to be a better idea, as the graphical representation of users, items, and their interactions could help us give more insights on the user item interaction semantics. So that's mostly from my side. Thank you.